Hi guys, this is Dr. Edwards again. So in this section, I'm going to extend the considerations that we've been already talking about on vectors, and particularly theorems associated with vector integration. There are three theorems that you need to at least have heard of, and therefore they will be less complicated for you when you have to use them in some setting. Particularly, you will find these theorems in your electricity and magnetism class and in classical mechanics as well. The first of these is called the divergence theorem or Gauss theorem. You see it go by both names. But here it's called the divergence theorem of Gauss. States that if the volume V is the volume bound by a closed surface, all right, so a closed surface like a basketball or the room that you're sitting in, and A is a vector function of position, XYZ, for instance, with continual derivatives, then the volume integral of the divergence of A, the first expression, is equal to the closed surface integral of A dot n ds, or go on and absorb the unit vector n in ds and then have the closed surface integral of A dot ds. That is the divergence theorem. And one can show that the left-hand side here is equal to the right-hand side. This is useful at some time where it may be simpler to compute the volume integral than it is to compute the surface integral. The second theorem here that I want to talk about is called Stokes' theorem. It states that if S is an open two-sided surface, like the tabletop that you may be sitting near on. So it's an open surface. Surface bound by a closed non-intersecting curve. So a curve all the way around the edge of your desktop, let's say. Then if A has continual derivatives in this space, then the closed line integral of A dot dr around that surface is equal to the surface integral over that surface. That's what both of these imply, of the curl of A dot ds. That is the Stokes theorem. And the last one I want to talk about here is called the Green theorem. And the Green theorem is in a plane, of course. If R is a closed region in the xy plane, and so these are xy coordinate system, bound by a simple closed curve C, and if M and N are continuous derivatives of x and y, having continual derivatives in this region, then the closed surface integral of what we call M dx plus the integral of n dy is equal to the surface integral of the partial of n with respect to x minus the partial m with respect to y, that quantity dx dy. So this is a surface integral here, and we can show in some problems that the left-hand side is equal to the right-hand side. So I'm going to go to a problem now that the author has done. This work is coming from my Shams outline book. So let me go to a problem that the author has done, number 2 here. And we're going to follow this number 2 problem and verify that the Green theorem is correct. We're going to show that you get the answer, a negative 1 over 20, using the theorem here, for the left-hand side being equal to the right-hand side. So verify green theorem in the plane of the closed line integral of the quantity xy plus y squared dx plus the quantity x squared dy, where C is a closed curve in the region bound by this straight line right here. That's the straight line. Y equals 2x. That makes it a straight line. The slope is 1, and the y-intercept is 0. And this parabolic curve, y equal to x squared. And you're going to go out to, the curve is bound out to the point 1, 1, starting at the point 0, 0. Okay, so let's now have it. You're going to do the left-hand side of the green theorem first. You're going to perform this integral. As I say to you over and over again, you can't do any integral without converting it back to the simple Riemann integral here. So this integral, the integrand has x and y, dx, and x here, dy. So we got to choose one or the other. And what we're going to do, we're going to effectively integrate along this curve, but we're just going to integrate along the x-axis from x equals 0 out to x equals 1. But we're going to substitute everywhere that we have y. We're going to put y equals x, put in x for y, and then we'll be able to perform the integral by effectively integrating straight along the x-axis. So that's what has happened here, where we have y, we put in x squared, y squared, put in that, you get x to the fourth. And then in the second case, you put that you have there. But notice that if you're going to integrate along this curve, along that curve, dy is equal to 2x dx. So that's where the 2x dx has come from here. He has substituted for this dy 2x dx. And now collect terms and simplify the integrand. And now you're ready to do a power law integration. The integral of the sum is the sum of the integrals and just power law. And I've seen that the author gets 19 over 20 for that part of the integration. The second part now is to integrate from 1, 1 back down along here. And let's see, which way does he choose to do that? He's going to still just integrate along the x-axis. Now, but what he notes is the following, that so n is equal to, okay, so let me see, what is he going to do? He's going to make the substitution. N is equal to x squared, and m is equal to the quantity x y plus y squared right there. Now he takes the partial of each of those, the partial with respect to of x squared with respect to x is equal to 2x, and the partial of this quantity with respect to y is equal to a negative x, and then you take that negative x from the 2x, that's how he gets the x there. And the partial of y squared with respect to y is equal to 2y. That's where he gets the 2y. Now see, so this is the quantity to be integrated over the surface that you have. And now, so since it's a double integral, we're going to integrate from the bottom curves up towards the top curve. So we're going to integrate from y x squared to y equals to x. Do that integral first. Therefore, he puts the dy in front of the dx. So you're going to integrate this expression. And then we'll integrate the x portion secondly. So he set it up now. He's ready to do the integral with respect to y. here, and we go on and perform that integration here, treating x as a constant, and then substitute in, and you get this expression here. Now the integral to be done, the final one, is from 0 to 1 for x. Now this is the function to be integrated, the quantity x to the 4th minus x cubed dx equals negative 1 over 20. So we get the same answer in both scenarios. So I want you then to read and go over this problem many times, review your surface integration if you need to. Make sure you understand why and how we got these two quantities here, the author got them. Then after you finish with a thorough review of this, I've given one homework problem as extra credit. It is problem 37 here. It is this problem 37 on page 132. So verify the green theorem in the plane. So now you're going to integrate in this plane, and you have to integrate this function here. So it is just like the problem we just finished with some small variation. But now you have to do the line integral on the left-hand side and the surface integral on the right-hand side. There are two answers, A and B. Answer for A, answer for B. So I want you to verify then the Green's theorem here. So keep in mind then there are these three important theorems that I wanted you to at least been exposed to just briefly. One is the divergence theorem, the Stokes theorem, and the Green theorem, okay? So go through these problems, all right? Then that's all for now.